These back-to-back classes are definitely weird. I go from statistics to calculus and it's kind of like a whiplash, but we get through it. Well, any questions at the moment, folks, while we're waiting it out? Okay. Well, it looks like we can start. Welcome back, everyone. So for today's class, we're extending everything we did with the chain rule to a new topic, implicit differentiation. Now, this topic is a little bit weird. What's going on with implicit differentiation is you have an implicit function, as strange as that sounds. The best way to talk about it is to kind of just jump right in, see how it goes. And maybe before that, let's review one problem with the chain rule because it's always a good reminder, no matter how weird 3.5 gets, it's really just the chain rule that we're using. So here's our really fast review problem. If we say y equals, let's make it be, how about a secant of x squared. So nothing too crazy to start us off. When you go to differentiate that thing, well, maybe before we go to differentiate it, always good advice for this is look before you leap. So this function right here will be outer. This is the function you would do last in order of operations. This function right here would be inner. And it's the function you would do first if you gave a value of x, say like 2, and ran through order of operations. So when we go to differentiate this thing, I'll just call it an ordinary y prime. First thing we handle is the derivative of secant. Anyone recall how secant comes out as a derivative? Exactly, we get a secant and a tangent. That's kind of a weird function when you differentiate. But that makes this one a kind of a tricky problem too. Derivative of secant is secant, leave a blank for the input, tangent, another blank for the input. Then the chain rule says, multiply that by the derivative of something. The something is going to be the inner function x squared, and it's going to go into 3 positions this time, only because the derivative of secant became secant and a tangent function. Does x squared have to go here and here at the same time? When it goes here, we differentiate it. So we navigated through the chain rule. Last thing to do is get to the end answer, y prime equals. I'll do this derivative first and put it out in front, 2x secant x squared tangent x squared. So that's the chain rule in action for us. Any questions, folks, on running through this one? Okay, so again, implicit differentiation is really just doing this kind of work, but it always looks different because we don't necessarily know what the exact function is. Even though we don't know what the function is, we can still differentiate it. So that's what we're going to try out very next. Any last questions before we go to the notes and wipe the annotation out? Okay, it's not gone forever. It's always on the video. So let's drop down to the notes here. Because implicit differentiation is weird enough, I want to do this question 2 different ways. The first way is just following your nose, do what you would probably normally do if you didn't want to worry about differentiating it implicitly. So we'll do this one from scratch by first principles. Then we're going to compare our answer to what happens in part B if we decide to really differentiate implicitly. Basically, example 1 is my cell of why you would want to differentiate implicitly. So let's start off. Here's our function. Y squared equals 5x to the power 4 minus x squared. And we want just the slope of the tangent line at 1, 2. Watch out for these instructions, basically, or especially on an exam. If it says just find the slope, that means your answer is m, whatever it turns out to be. You don't actually need the tangent line equation, so you could stop sooner on this one. Before we do that, it's a good idea to say, what does the function look like? In fact, I can't even say the function, that's using the definite article. There's multiple functions inside there. That's half of why we call it an implicit differentiation. So let's throw this into Desmos and just see what it looks like. It goes y squared equals 5x to the power 4 minus x squared. So that's the graph of this curve, is the best way to call it now. This does not pass the vertical line test at all. It means it's not the graph of a function. There's two functions that's really inside there. So that's the kind of conundrum we have to work around in implicit differentiation. It says we want the slope at 1, 2. So that will be right about here. So all I can tell you for sure is we put a tangent line right at that red dot at exactly 1, 2. Oh, there we go. Then they'll have a positive slope for sure. If I can get it to stay there. That makes sense to folks at the moment? Okay, let me take a screenshot of this. We'll throw it on our page just so we have a curve to look at. And you know what? That actually helps to solve this and go through the motions. So we want the slope to the tangent line that's going to be right here. First thing we're going to do, take this equation and find out which is the actual function we'll be differentiating there. Because once again, there's two functions hidden here because the power on y was 2. If this was, say, y to the power 5, expect 5 different functions to produce that entire curve. So it's not so bad. We go to y squared equals 5x power 4 minus x squared. If we're trying to solve for the function y, to get the explicit function, we just square root both sides. On the left will be y equals 2 different versions because we took a square root, either a positive or a negative answer, and then 5x power 4 minus x squared. Now, this is still no good for us because I don't want to differentiate 2 functions. There's only one function we actually need. Anyone see which it'll be? The positive root or the negative? I heard positive? Absolutely. And the reason it's positive is because this second coordinate 2 is positive itself, is what's taking us to that positive root right there. If it was 1, negative 2, we'd have been down here, and we'd have used the negative sign in our answer. So now we have a function. The explicit, as opposed to implicit, function is f of x equals root 5x power 4 minus x squared. Now that's something we can work with. We can differentiate that, throw in the value of 1, and we'll get a slope out. Any questions before we give those steps a try? Okay, differentiating this, it's still a chain rule. Just because we found the explicit function doesn't mean we're escaping the chain rule. We're going to do it one way or another. But the next thing I want to show is if you have this as the inner function and your outer function is the square root, there is a bit of a shortcut to working through this derivative. I'll show it once down here, and then we'll apply that shortcut. So suppose your function is y equals root x, and you want to differentiate that thing. Imagine what steps you would take. Say we're in section 3.1. You would want to say, what is the exponent on that x? It's a power of 1/2. So that's the first thing we'll do. Next thing we'll do is differentiate. So we'll say y prime equals. First thing that happens is by the power rule, 1/2 comes down. The new power of x is 1 less. So it's going to be 1/2 minus 1. And then this becomes 1/2 x to the power of negative 1/2. That's a fine derivative as it stands right there. But if you wanted to, you can simplify it. And sometimes there is value in doing that. So let's say on our next line, I'm going to force this exponent to become positive. We just throw it down under the denominator, into the denominator, and get 1 over 2x to the power positive 1/2. Final thing to do is if you prefer square roots, notationally for your exponent, I'll bring in the root x on our next step. So y prime equals 1 over 2 root x. That makes sense to folks on getting that final form of the derivative there. Awesome. So If you did these steps each and every time, that's not bad at all. You get really fluent at it, you know exactly how it works. But then to some extent, it'll feel like you're reinventing the wheel over and over again when you differentiate square root x. So here's the formula I propose. A really, really helpful formula goes like this. The derivative with respect to x of square root x always turns into 1 over 2 root x. And that's just a nice formula to have at hand. We're about to use it right here. We need to take the derivative of a square root. So let's apply it right now. So back to finding the slope at that point right here. We found an explicit function. We've analyzed what we do with the chain rule. So the derivative f prime at x will be, first differentiate the outer function. Let me change to this color since we're using this formula. For every square root, it'll go 1 over 2 square root of something. So we've handled that function there. By the chain rule, there'll be the derivative of 1 extra piece. Let's pause right here. Does that make sense in purple with our formula and the black portion through chain rule so far? Awesome, glad to hear that. Next thing we do is we just throw in some values. Whatever the inner function is, it goes into the space holders we put in. So 5x power 4 minus x squared goes here and here. Now this whole thing in parentheses, I'm going to multiply up into the numerator while we calculate this. So it's going to just wipe out this 1 when it multiplies. And our derivative f prime at x is now equal to, upon differentiating, the 4 will come down, multiplying 5, so 20, x power 3. And same little number game on this one. 2 comes down, multiplying the negative 1, so negative 2, x power 1, best just left as an x. Below, I'm now just copying, is 2 root 5x power 4 minus x squared. And if you wanted to, this one does reduce. You can take this 2 and divide it out of the denominator. We'll just be forced to divide into the numerator. That will become 10. And that will become just a negative x. If you divide in this way, you just have to make sure to divide all terms in the numerator and all terms in the denominator. There's only one term. So we have now 10x cubed minus x divided by the square root 5x power 4 minus x squared. So that's finally our derivative. It'll give us the slope of the tangent line, not at every point of this curve, only on the part of this curve that goes from here and up and here and up, because that's the positive root version right here. It won't give us the slope on anything down below because we didn't specify that function. That's okay if we want to find the slope. We'll say that m for slope is going to be the derivative evaluated at the first coordinate of 1. I switch colors, let me try again. So here's what happens to it. We'll plug a 1 here. It's going to be just a 10 minus 1 in the numerator, so a value of 9. Plug 1 inside here, it'll become 5 minus 1 inside the square root in the denominator, so that's square root of 4. So the slope is 9/2. You know, I believe that it's definitely positive and it definitely looks steep. So 9/2 about 4.5. I said about exactly 4.5 looks like the right slope for this. That's quite a process, right? If we have a curve to specify it in a strange way, and we want to still do calculus, there's 2 options. Find the right explicit portion of the curve that we can get a function out of, and then work with that. Or we can do it by implicit differentiation. This is way weirder, but it's actually much more efficient. And well, if it's more efficient, it's going to be more accurate since I'm not taking all of these additional steps to get through it. Any questions at all, folks, before we turn to implicit differentiation? Okay, so again, we go to this original curve. Oh, I guess it's already pasted down right here. And when we do implicit differentiation, we're just going to differentiate the left-hand side and the right-hand side immediately. So first I'll copy down the equation with a little bit of space around equality. The first step in implicit differentiation is to do this. I'll take the derivative, just trying to figure a color, black ought to be fine. I'll take the derivative with respect to x on the left-hand side in this way, and the derivative with respect to x on the right-hand side going this way. Now the right-hand side is not bad. We've done it before, right? We differentiate, that's right here through the chain rule. It's the left-hand side that is really, really weird. So let's take some time with that. Let's put this on a new page even. And I want to split this off. My right-hand column is going to be my explanation of why implicit differentiation goes the way it does. And like we've been hinting at, it's all about the chain rule. So when you see a function like y squared, well, y is a function of x. There's just happens to be multiple functions there, but there is one implicit function, and there it is. Let's actually indicate that. This is the implicit function. What makes it implicit? It's the fact I don't have a formula for it. And you could solve it, but if the equation was harder, and we'll see one, you absolutely would not want to solve it. It might not be solvable. You'd only be doing approximate solutions. What made this function explicit right here is we actually had a formula for it. We wrote it out. But even though we don't have the exact function, we can still differentiate y squared. Here's how it's going to go. If y is equal to f of x, then we'll say dy dx is equal to f prime at x. So that's a warm up. We'll use that as we get through this. Now let's return to this right here. If y is equal to f of x, that means y squared is f of x. Here's where we probably want some good colors. F of x here to the power of 2. So that's how it could be written out if y is f of x. But the moment you write out this much, let me fix that exponent, it should look like a 2. We have a notion of inner and outer function once again. Anyone see which function is inner in this setup here? Absolutely. So f of x will be considered the inner function, which means the squaring function, the power 2 function, will be the outer. So let's differentiate that right here and right now and see just what happens to it. So on this line, I'm going to write d by dx. I'm just saying the derivative with respect to x of y squared. You could have just said y squared of the prime outside the parentheses. So we're now doing the left-hand side here. Over here through the chain rule, here's how it goes. We differentiate the outer function first. Because it's a squaring function, 2 comes down. Let me try again with those brackets. 2 comes down as a coefficient. The new exponent is 1, so we'll drop that in a moment. And the inner function, or let me first put this here. So we pull the 2 down by the power rule, new power of 1, and we're going to multiply by a derivative through the chain rule, our typical kind of setup steps. Then the inner function f of x goes in both of those blanks. Again, same thing we've been doing all along, including our warm-up question. They'll go here and here. Well, we're just about there. Next thing to do is we go back to y equals f of x. We're going to make some substitutions. On this, the derivative of x, derivative with respect to x of y squared will become 2. This f of x, we're just going to throw in a y. Y is just the shorter way to refer to it. This f prime of x right here, we're going to throw in dy dx. So those are our 2 replacements highlighted in yellow. This right here is the punchline of implicit differentiation. If you know your function, your variable y is a function of x, then when you differentiate this, you're really doing the chain rule in this format. So derivative of y squared will cause a power of 2 right over here on the left to come down where y was. The new power of y is 1, so we just leave it as a 2y. And that's not so bad, right? We expect 2 to come down and the new exponent to be y. But what we don't always expect is this portion, times dy dx. So if you differentiate a variable y with respect to x, you are using the chain rule. You first differentiate normally, like if it was x. But then the chain rule says you multiply by the derivative of y right here. And we did it over here as well on the right-hand column. So that's finally the idea of implicit differentiation. It's also a little bit weird, and for a lot of people, I think, me certainly when I was learning this is the one spot in calculus where I felt like it was always a little bit foggy until I had to teach it and then really see what was going on with that stuff. Well, any questions at all, folks, on the 2y times dy dx? Okay, on the right-hand side is the explanation, and it's also a good explanation of why we don't do it this way. It takes a lot of writing just to explain what happens on the right-hand side. On the left-hand side, this is the implicit differentiation that takes a shortcut route through all of those steps on the right column. Then on the opposite end of the equation, if you differentiate that, well, we've done it before, you get 20x cubed minus 2x. Now, we did a lot of stuff here, but imagine the left-hand column is all you would ever write if you were solving this problem on, say, a homework problem. This is just explanatory on the right-hand side. Our goal is to find the derivative dy dx. So let's just divide by 2y. dy dx is now 20x cubed minus 2x, divide by 2y. This one will simplify. We can divide 2 here, here, and here. So now we can say it's equal to 10x cubed minus x divided by y. You know, we're just about done. We wanted just the slope of the tangent line, and we wanted it at coordinates 1, 2. You know, I shouldn't put too much stuff in yellow, or this yellow starts to lose its meaning. But this 1, 2 is actually kind of tricky, because when we look at the form of our derivative, it's different, right? It's of 2 variables, x and y. So the slope m will be the derivative of y with respect to x. This is given implicitly because we don't even know what y is unless you turn up where we solved it. Imagine we didn't even do any of that. So we give it up here, once I get that dot to settle, x equals 1, y equals 2. So on this evaluation bar, we're evaluating for 2 variables at once, and that's how it would be indicated. If there was more variables, we would just add more conditions on what the evaluation turns into.
Question.
Yeah, go ahead. It came from that point up there. And now that thank you for mentioning that. That's worth highlighting right here for sure. The 1 and 2 came from the original point, the x and y coordinate. Does that make sense so far?
Yeah.
Awesome. Oh no, I'm glad you asked that question there. That's really kind of the extra trickiness on implicit differentiation here so far. But now we'll plug a 1 in there for x. It'll be 10 minus 1 again. So just 10. You know, it might be a good idea to go like this, just because this one's a little bit trickier. So here I've just put blanks for the x variable where 1 is going in that kind of way. And then for the y variable, we're throwing in a 2. And so that's what the evaluation looks like this time. The numerator, it's 9 divided by 2. And somehow, some way, we've gotten the exact same slope. Let me double check. Yeah, we got 9/2 up here as well. It wasn't a coincidence, but this is kind of the magic of implicit differentiation. I didn't even know what the curve looks like on this solution in part B, but in part A, you absolutely have to have some idea of where you are in the geometry of the curve right here, or else you can't really get through this. It's a pot shot. Here, our derivative came out in this format. That's the explicit derivative because y is specified. But over here, I have no clue what y is, so that derivative is in implicit form now. But it doesn't matter. Even though y is completely unsolved for, this will still give you the slope of the tangent line at every single point of that original curve. Even if you're on the bottom end right here, it doesn't matter. If it's a valid point, get its coordinates, plug it in, and you will get a slope. So implicit differentiation is not only more efficient, it's more powerful than when we did it explicitly. I have limited results in our part A, but this gives us slope everywhere, except where there'd be a vertical tangent line. That slope is undefined. Any questions at all, folks, with the implicit method? Yeah. I would say the big giveaway, I'm glad you asked that question, is this right here. The power of 2 on y means we don't really have y as a function of x. It's not solved for yet. So this indicates, actually this is a better pen to use here, indicates implicit differentiation. That's a long word, since y is not isolated. And we can isolate it, right? We could have taken the square root like we did in part A, but in some problems that is a lot harder or potentially even impossible. Unless we used implicit differentiation, we may not be able to find the derivative or find a slope like we did here. Other questions at the moment? Yeah.
We're solving for 2y dx. Sorry, what is that exactly? Does it mean that what's on the right side is the derivative that like all extend?
Exactly. It's the derivative with respect to x. Yes. You could have called it, if you wanted to, y prime. Exactly. Question up here?
So these are the problems with this all the rest of the systems to divide dx equals the derivative over 2y.
Go right to here? Yeah, absolutely. Everything on the right-hand side was really just meant to explain that right there. Why you also get a dy dx. Yeah, exactly. Just some logic on that portion there. But when we go to do this on the follow-up example 2, we're going to do exactly what you mentioned. We're going to just dive right into that. Other questions at the moment? Yeah, go ahead. If y is isolated, you could still use it, but nothing special would happen right here. You would lose this and you would only get dy dx if y was isolated. So if y isn't isolated, you're really just differentiating normally. Yeah, go ahead.
Which also is then similar to square root of y.
Sorry, say again.
Which is then similar to square root of y.
Yeah, absolutely. Anything that's around y, like cosine y, square root of y, e to the y, those are all those kinds of problems, which is giving us implicit differentiation. Other questions or concepts so far? Yeah. Oh, absolutely. So if you want to do it in Newton notation, you could have put in, let me just highlight the regions, right here and right here. You could have just put in a y prime and that would have been just fine. Is that what you were asking about? The very first thing right here? Oh, if you wanted that in Newton's notation, let me clear this and this. Sorry, deleting is kind of tricky. You could have written it out in this way. Just put a prime on that and a prime on that, and that would have been just fine as well. In fact, I'll leave the notes just like this because that's really just a stylistic choice to start out, whether you're using primes or d by dx's. Other questions at the moment? Yeah.
Let's make sure I get the Leibniz notation. Say it was t equals 5a, cubed, whatever it may be, and you would write d of t over d of a.
Yeah, exactly. Exactly. Think of your dependent variable as the one on top, independent of the one on bottom. Exactly. Other questions or comments so far? Okay, well, we definitely have to try out another one, right? So let's go to example 2. Let's see what other wild stuff we're going to get into. This one I don't want to make too nasty, so let's go something that's still sort of a warm-up. I'll call this one part A. And the next one will be just a little bit worse, so that'll be our part B. For this one, let's put in 2y cubed plus y squared minus y to the power of 5. Kind of strange order of the exponents there, but it could be written any way they like. And on the right-hand side, it's x power 4 minus 2x cubed plus x squared. All we're doing here is calculating dy dx, or y prime if you prefer. So we're not finding the slope, we're just getting a derivative this time. And it's always kind of interesting when you do these problems to consider what is the graph of this thing. I mean, it's wild looking, right? So let's go to Desmos and just take a look at that thing. So going left to right, this is 2y cubed plus y squared minus y to the power 5 equals, and as we type this in, we start to get curves. This is if it was x, now power 4, looks like a crazy hanger, minus 2x cubed. That almost looks like a face, I'm not really sure. It's like looking at clouds, plus x squared, and it goes back to that shape. So that's our curve. Really weird, right? Yeah, I could see that. Yeah, it's like a wagon cresting a hill. Kind of interesting curve. They should call this the wagon curve or something like that. So let's put this in. And although it's maybe not the biggest help at getting through this one, it's always good to know what in the world are you doing when you differentiate implicitly. And if you have a picture, it does help. So when we calculate dy dx, we'll go back to this picture here. Okay, let's give this a try then. I'm going to start by just recopying the equation so you'll know that was the original question right here. Let's go 2y cubed plus y squared minus y to the power 5. Or I'll use Newton's prime and say we're differentiating left-hand side, which forces us to differentiate the right-hand side as well. So this is the format it would take. Now, the warning is if you're using implicit differentiation and y is a function of x, like in this case, every time you differentiate y, every single time, there will be a dy dx that comes out, or a y prime if you're using prime notation. So right off of this red dot, the power rule says 3 will come down, multiplying the 2, giving us 6, y to the power of 1 less, so y squared. But y is a function of x, so we have to multiply by the derivative of y through the chain rule. And here it is, dy dx. And just to emphasize, I like the dy dx for implicit differentiation. It's a personal choice. If you put in a y prime, that's totally fine. Does that make sense on that first term right here? Okay, then we do it again. This one is y squared. It involves y, so this will be plus 2y times dy dx. Because there was a variable y, that y squared is really some function f of x to the power of 2, where y equals f of x. So we get the 2y, and then we multiply by the inner function dy dx as a derivative. So that takes care of the left-hand side, or nope, there is one more term, that one. Anyone see what that would come out as? Anyone have the answer for that portion? Yeah, go ahead. Exactly. Implicit differentiation is definitely weird, but if you see this pattern that there's a variable y, so you put in dy dx, then you are in definitely good shape. Now the right-hand side, definitely much nicer because it only involves a variable x. This is differentiation as normal. So 4x cubed minus, here will be 6x squared plus a 2x. So we've got it. Well, that's the full derivative, but we want to solve for dy dx. So that's what the instructions are indicating when it says compute dy dx. Any questions at the moment to this stage? Because if it's a variable x, we only put in the normal derivative. If it's a variable y, it's really a function of x, y equals f of x. And that's why we have to multiply by its derivative right here. But if it's just the x variable, you differentiate as normally you would in the prior sections. Other questions at the moment? Okay, I would like that you asked that question because just for a preview of what's coming, when we're in a section related rates in this chapter 3, I think it's 3.9 or yeah, I think it's 3.9. We'll have that x is a function of time, y is some function of time as well, some other function. And when we differentiate implicitly, even when we differentiate the x variable, we're going to get a dx dt. But the reason nothing happened over here, it's just 4x cubed, is because x is not a function of something else, it's only a variable. This is the sole reason we're picking up the dy dx. So we'll return to that thought when we're in section 3.9 on related rates. Other questions at the moment? Okay, well, we're practically done. Next thing we do is factor dy dx. I'm going to factor it off to the right-hand side. So it's going to be 6y squared plus 2y minus 5y to the power 4 dy dx equals 4x cubed minus 6x squared plus 2x. Now it's just one step away. We solve for dy dx the moment we divide by that group on the left. So the derivative of a function y, again, I say the function, but there's at most 5 of them, with respect to x, is 4x cubed minus 6x squared plus 2x, all of which is divided by 6y squared plus 2y minus 5y to the power of 4. Whew, we got it, folks? This weird object right here, here's what it does. Pick any point on the graph. Maybe it's this point on the wagon right here. If you can tell me the exact x and y coordinates, just plug them in, and that will give you the slope of the tangent line right at this location. Yeah, go ahead.
Is there a way to decide x and y coordinates?
Oh yeah, you could say, for example, if you knew that you wanted a point where x equals 2, you would plug 2 here, 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 and then solve for y, which is not fun. That's a degree 5 polynomial. You're solving for y might have to be an approximated method, because there's this weird fact in algebra. They have proven the non-existence of a degree 5 solution to polynomials. There's a quadratic formula, there's a cubic formula, there's a degree 4 formula. But algebra has said, and they found out, there is no degree 5 formula. So you might have to actually approximate the solution to the y coordinate once you pick an x coordinate. So if you want exact values, it's going to be really, really hard. So you might have to settle for approximate coordinates right here and know that you are getting an approximate slope coming out. Yeah, go ahead.
The fact that doesn't exist, is that a reflection of the nature of the universe, or is that a reflection of limits of algebra?
I would say limits of algebra primarily. And the physicists might say that's also connotated with the limits of the universe. But it comes from, if you're really curious about the non-existence of that polynomial, it's Galois theory. So some guy, he was a mathematician, I think he was in his 20s. He wrote down some extremely abstract algebra that nobody knew about. The next day he gets in a duel and is shot to death. Someone published his papers and it came out as Galois theory. And one of the consequences is a degree 5 polynomial. The generic ones have no solutions whatsoever. Very, very bizarre. I'll put that in parentheses as a side comment there. But other questions about that so far? Okay, so it's all very weird stuff. I mean, it's magical in a sense. Find an exact coordinate and you've got a slope, but like folks are mentioning in class, getting an exact coordinate is kind of a difficult thing to do all on its own. Other questions so far with this one? Okay, I think I might have asked that twice. How about we try a harder one next? Does that sound all right to folks? Okay, so let's try something that's slightly worse. This one will be our part B. On our part B, let me grab the function. It goes y sine x squared equals x sine y squared. Well, I said grab the function, but it's really just a curve. And it's a weird curve. We have periodic functions inside here. The moment you put in periodic functions, all sorts of weird things can happen. So let's get a look at what this curve looks like, or take a look at it. So we'll start with y sine x to the power 2 equals x, already looks weird, sine y squared. So there it is. And again, this is where implicit differentiation really kind of shines. There is infinitely many functions here. So if we take this equation contains fine detail that has not been fully resolved. There's probably more stuff inside here that we can't even see. Let's see if we can zoom in. Maybe not. Who knows? The axes are overlaid with red, both the x and y axis, so that might be part of this curve as well. But here it is. We're going to differentiate that thing. Again, that's why implicit differentiation is so powerful. If you had an applied process, maybe you're looking at vibrations on a bridge that had a cyclic nature, probably wouldn't be this crazy. But if this problem was important to you, and you could approximate one of these coordinates, then the derivative of this will give you the right slope. So let's give it a try. Any questions first? Yeah, if you think of this as a field almost, it's almost looking kind of like that. Yeah, weird functions. And again, that's the interesting nature of implicit differentiation. We don't even need to know which of these curves we're even on. But that's okay. Let's go ahead and differentiate it regardless. So we're going to start off by going d dx of the left-hand side, y sine x squared. Then the derivative d dx of the right-hand side, x sine y squared. But now when we write out this derivative, we have other problems. Right here is a product rule. So when we go to differentiate the left-hand side, it has to be reflected as a product rule. Let's be really careful with this one as we go to write it out. We'll go for product rule. 4 sets of parentheses, paired up, cross addition. And that'll take care of the left-hand side. Same issue over here. We have a function x multiplying sine y squared. So we need to set up a product rule here. And let me try one more time with my parentheses. It doesn't look like that's going to fit with my strategy. So one more attempt. Also forgot my prime symbols. Let me put these in as I go. Okay, so that handles both the left-hand side and the right-hand side through the product rule. Now think of this as a first function, that is the second function. Throwing those in, we'll get y and y. Sine x squared. Sine x squared. And then just do it all over again on the right-hand side. The functions go x and sine y squared. So x here and here. Sine y squared goes here and here. So we've got it, folks. That's our setup of the product rule on both sides of the equation. Any questions to this stage so far? Okay, as we go to differentiate, here, this one's not so bad. The derivative does not turn into a 1 because that's a function of x. Y prime, we could just leave as a y prime or call it a dy dx. I'll go with the dy dx. So there it is. We differentiated y. Then this one copies sine x squared. Over here, we're going to just copy in a y, so plus y. But right here, that derivative, we need to be extra careful. That one's a chain rule just out of nowhere. So we'll need to be very careful on how to analyze. Which function would you all say is outer function? Is it sine or x squared on that one? Good call. So sine is our first one to differentiate. The outer. X squared will be the second one, or the inner. Now, let's go ahead and crank that out. Derivative of sine turns into a cosine. Then we multiply by a new derivative through the chain rule here. Last thing to do is copy in that x squared. So we'll go here and here. And you know, the left-hand side is just about done. That derivative where x squared prime is indicated, that'll just turn into a 2x. So we're in good shape for that. Now let's come over here and crank out the left-hand side. Derivative of x will just turn into a 1. It didn't happen to y because y equals f of x, truly. So here we're saying derivative of that function. But if it's just a variable, it becomes a 1. Then we're copying in sine y squared. Copy the x. And now this is a new chain rule. But this chain rule is much worse. There are 3 functions inside there. Here's how it kind of organizes this time. The outermost function is sine, like before. Then the squaring function, that's the middle function. Then finally, the third function, if I can find a spot to put it, let's put it maybe here. This one is inner. It's the function y equals f of x itself. So we've done one of these before where there's 3 derivatives to get through. Let's try it out again and see how we feel about it. So let's go in order. Derivative of sine will turn into a cosine. Then we will need to multiply by the derivative of that input. But let's try that one-shot method, taking a shortcut, and let me know how you feel about it. I'm absolutely happy to show it a different way. We want to do this in one shot. You take the derivative of sine, it comes in as cosine. You copy in the input to cosine, which was y squared, unadulterated, so there it is. Then the 2 is telling us differentiate the middle function. So in other words, we're differentiating y squared. That'll take a power 2 to come down. New power on y is 1. But there is a next derivative. We multiply by the derivative of the inner function, which is just y itself, and it will look like this. dy dx. So that is skipping some steps. How do folks feel about that? Should we unwind it and see it a different way, or does it make sense? Let's see those extra steps. Awesome. If you're happy doing it in this way, you're always welcome to do it. But I agree, this is a lot going on. Let's do the same kind of strategy we did over here. Let's break down the chain rule a little bit better. So if we unwind it and try again, let's go one stage at a time. Take the derivative of sine, you get a cosine. Put in a blank here. Another blank right here, because we're about to use the chain rule. So same thing I did like over here when we did cosine. Go to the interior. We're going to copy y squared into this location and this location. So now we're in a good shape. We only have 2 derivatives to get through. This one here, that's an ordinary derivative giving a 2x. This one is implicit differentiation, or it's really still chain rule. The outer function's 2, the inner function is y itself. So we'll handle that on our next step. Any questions at all, folks, to this stage? Okay, let's run through it. We have a dy dx. Traditionally, it's better to have your dy dx come as the last factor. So I'll put sine x squared first. Reason we do that is it avoids a miscommunication. We're not saying the derivative is affecting sine x squared. We're not saying it here, but we're being more clear if the derivative ends right there in Leibniz. Then over here, I'll differentiate x squared and go plus 2xy. I moved the 2x in front of the y, just brought them together. Cosine x squared can copy in. Going off to the right, we have just a sine y squared. And now here's where we're going to be careful. I'm just going to copy plus x cosine y squared. I'll close the parenthesis just to be specific. Everything else is not going inside cosine. Now when we're differentiating y squared, this is ordinary implicit differentiation. It'll turn into a 2y. Let me keep it in green to show where that's going. But because y is a function of x, we multiply it by dy dx once again. So that finally does it, folks. That's the end of all the calculus. Now we have to solve for dy dx. It appears in two locations for this equation. Any questions at all, folks, to this stage? Okay, so my goal is to get dy dx, which appears here and here, onto just one side of the equation. So I'll keep this one right where it is. I'll subtract the x cosine y squared 2y dy dx from both sides of that equation. So it's sine x squared dy dx. I'm subtracting this whole thing. I'm going to put the 2yx together, so it'll be minus 2. I'll go xy just to keep the same format. Then cosine y squared. And then the dy dx. So I've taken this, subtracted it to that side of the equation, resulting in that. Does that look right to folks? Okay. Easiest mistake to make at this stage of the work is just not copying something, because there are tons of variables and constants and signs. So it's good to be really methodical at this stage. Next thing I'm going to do is subtract that from both sides of the equation. So sine y squared is going to stay put right where it's at. Then subtract 2xy cosine x squared. Thank goodness there's more space, so we're just about there, folks. When this happens, we kind of know what to do. We just factor out a dy dx. I'll factor it to the right, and then we'll divide by whatever survived after the factoring. Any questions to this stage? Yeah, go ahead.
Can you subtract that just so you can have your dy dx on one side?
Exactly, yeah. So once we factor it, it's going to emerge in just one location, thereby solving it. So let's do that factoring step. We'll have sine x squared minus 2xy cosine y squared multiplying dy dx. The right hand side is just the same, still sine y squared minus 2xy cosine x squared. And then finally, I'm dividing by this entire parenthesis here by the red dot. We have an answer of the derivative of those functions y. There's infinitely many this time because of the periodicity of the trig functions. Dy dx is equal to that whole numerator right there, sine y squared minus 2xy cosine x squared, divided by that entire group that was left over from factoring. So divide by sine x squared minus 2xy cosine y squared. Finally, that's where that problem sits after a lot of good work on this one. Let's see if we can zoom out and show the original question. Well, we did it, folks. This curve is just ridiculous. It doesn't even plot nicely in Desmos. It takes a lot of computation just to display it. But if it's a problem near and dear to your heart, if you can find a point on here, that's even harder than what we've done. Plug that point right here, and you will get the exact slope of the tangent line at any position of this wild looking curve. Well, that's the whole idea of implicit differentiation. Now, I think the biggest questions people have when you see this is, what does it look like on an exam? I could never give you this on a real exam, right? That's crazy, and it wouldn't be fun to grade either. I'll let you know that. That'd have to be like a 2-hour exam or something. A real exam question would look more like this one right here. I would give you a curve, something not crazy. This is not too bad. and ask you to find, say, this time it's the equation of the tangent line at a specific point. This one's pretty similar to a homework question, so I think this is a good one to end on. But any questions first on what we did up here? Okay, let's try this out again. We worked hard on this one, so this one's kind of like a break. If you saw this on an exam, I'm going to print the curve as well. It's really just to kind of help you out. There's like an internal check built in if we understand what's being said here. So this curve is called the devil's curve. I have no idea why. It's given by that specific equation. And we want to find the equation of the tangent line at 0, -2. That would be right here. You know what? We have the equation of that tangent line. Anyone know what it is? Exactly. It's horizontal, so it's y = 0. Doesn't mean we're done, right? For the full credit, we still have to actually use implicit differentiation to double check we really have the right tangent line. But if we have y = 0, that means our derivative is expected to be 0. Or hang on, I did make a mistake on that. The slope is 0, but what's the equation of the tangent line? Exactly, it's at height -2 because of this right here. So I should have said y = -2. I think I got confused with the slope being 0 as opposed to the equation. Sorry for that confusion there. Well, let's give this a try. If you were to differentiate that implicitly, it's not a good time because it's a product rule again on both sides of the equation, right? But you can manipulate these things algebraically if it helps us. So let's just distribute y squared inside. We get y power 4 minus 4y squared. Distribute x squared inside as well on the right-hand side. And we get x power 4 minus 5x squared. Now, there's all sorts of styles in doing the next steps. Let's use Newton's prime notation. We haven't been giving it a lot of love this class. So derivative on the left with the prime, and on the right with the prime. Now, again, never forget implicit differentiation is always, really you're just doing the chain rule. So if you differentiate this, the outer function is the power 4 function. You get 4y³. But then you multiply by the derivative of the inner function, which is y. We don't know what it is, we haven't solved for it. But we could put a dy dx here, or if you like a y prime, totally up to you. Is that all right with folks, putting y prime here on this problem? Okay, I'd like it because it's a little bit faster. The reason I've been focusing on the dy dx's is it'll be helpful when we're in section 3.9, where it's a really good idea to have Leibniz notation when both x and y are a function of some other variable. But here, that one's done. We just do it again over here. 2 comes down and multiplies, giving us a -8. New power on y is 1. I'll drop the exponent on the next step. Multiply by the derivative of the function inside, which is y, and it looks like this. Times y prime. I'll highlight these because this is what we get from implicit differentiation, matching the highlighting here. But this is a variable x. It's not a function of something else. So it's an ordinary derivative. This one will be 4x³. And this one will become -10x. That means this one's just about done. You can factor out y prime to the right-hand side and get 4y³ minus 8y times our y prime equals 4x³ minus 10x. And last thing to do, divide both sides by the group on the left. You have that y prime will be equal to 4x³ minus 10x, divide by 4y³ minus 8y. Well, if we want to get the equation of the tangent line, we have the major thing we needed. We needed the derivative right away. So that's the first thing you have to calculate. Let's call that a step 1. Step 2, we need to find the slope. So the slope m would be equal to this y prime at x equals 0 right here, and y equals -2, coming from that original point. Let's highlight these just to be specific. If we wrote this out in Leibniz notation, that's where we would have done the vertical bar and put x equals 0, y equals -2. Here, what we're going to do is say m equals. I'm going to put in some placeholders for where the variables were. And in the denominator, we'll go -2, -2. Now, thing to note about the denominator is that's -8/4, so -32 plus 16. The denominator is not 0, so that's good for us. Now, the numerator, we're plugging in 0 here and 0 here. That means the numerator is 0, the whole thing is 0, and it is defined. We got a 0 down below. That means you might have been looking for a tangent line right here, which would have been vertical. You would have the division by 0 right in that location if it was a vertical tangent line. But here, if our horizontal tangent line is what we're expecting, we should get a 0 slope. That means the equation is just automatically y equals -2. But if you want to go through the motions, suppose it was an exam and the equation was a little more complicated. You might want to go y minus y1 equals slope times x minus x1, just to be careful. Then we have a value for x1, it's 0. We have a value for y1, it's -2. And we even have a value for the slope. So it becomes y minus, I'm going to grab that -2 again, equals the slope m, which is 0, times x minus, I'll plug this in just to say we did, but it's just still 0. Then last thing, we have y plus 2 equals 0, and so y equals -2. That's the thing we were trying to find, and the thing that we were kind of expecting based off this graph right here. So the equation of the tangent line to the devil's curve at 0, -2 is just that, a horizontal line at height -2. Kind of a weird curve, but this is kind of more like what the equations would look like if we were doing this in an exam setting. It's got to be pretty directed and pretty fast. The algebra can't go crazy. But if it's a homework problem, there could be stuff about like this. I don't think there's any one problem as bad as this, but there is one on the homework that's pretty close to it. It's something like x sine y or something like that. Well, any last questions, folks, on getting through this problem here? Okay, well, with what I had for the notes, I did have 2 types of application problems. You could use implicit differentiation to calculate a second derivative. This one's not on the homework, it was just if we had extra time. This is the actual bigger application. One major reason why we love implicit differentiation is it will allow you to calculate the derivative of an inverse function. Natural log x is inverse to y equals e to the x. So now we can do derivatives of logarithms. You'll notice we skipped those until now. We can also do derivatives of sine inverse, cosine inverse, tangent inverse, and so on. Implicit differentiation gives you the tools to handle all of these weird kind of cases. The very next section we're going into is derivatives of logarithms. So if we don't do this problem today, that would probably be our first problem when we come back next Monday. Show how to differentiate natural log x implicitly. So I think we're probably in a good stopping point. The rest of my questions are at least 10 minutes long. Any last questions, folks, before we call it a night? Okay, well, have a great weekend, everyone. Your assignment number, which one was it? 3, which was just a section 2.8, is due today. You can hand it in here or email me later. That would always be fine. And we're going to our normal routine of more normal assignments. This one looks pretty terrible, but these are through the differentiation rules, so they're a lot faster than they actually look. Well, have a great weekend, folks. I'll see you all next week.